So counting, not as easy as it sounds because, counting 1, 2, 3, 4, 5, not quite that. But if you think about it as the ability to count large quantities fairly quickly, that's probably a kind of a reasonable definition. But we really just look at it as these three different types of calculations: factorials, permutations, and combinations. All right. So you see this information down here. We'll get to that in a minute. But I like to start off with a guided example first, because I think it kind of drives the point home. A group of 3 people must be arranged in a line. How many possible arrangements are there? Right. So when you think about the term arrangement, the order is important. Right. So the order is important for when you're dealing with an arrangement. I think of it like an arrangement of flowers. Like I went to the florist recently, and it's like, because I'm not really good with that sort of stuff, So fortunately, the guy was very, very accommodating. He's like, "So what do you want?" I was like, "I have no idea. What color? Give me a color. Give me a type of flower." So long story short, there's like 3, 4 different types of flowers in there, and like it's called an arrangement. Because why? You don't just dump one type of flower on top of the other and just hope for the best. You place them in very specific ways so that it's more visually appealing, right? So that's always kind of how I remembered arrangement, like what it means contextually. Because if I just said, give me a group, not an arrangement, but a group of 3 different types of flowers, then it really doesn't matter what order they're in. Just as long as you hand me a group of 3 different types of flowers, we're good. All right. So that's kind of like my everyday example for the meaning of that. But if you want to get into a practical sense or a practical approach, we have 3 people. I'll just call them person A, person B, person C. So A, B, and C. All right. There's a few different ways we can handle this. And ultimately, it's going to lead to the concept of a factorial. But let me just start in the most basic sense. So we could manually arrange these individuals. So if you have person A, person B, person C, those are the people that you have available. I can put them in any order I want. Right. So maybe I want the B to come first and the A to come at the end. Maybe I want the C to come first and the B to be at the end. All these are possibilities. All right. And another way that they might ask this question, whoever they are, is if you have a word, how many different ways can you rearrange the letters in the word? That's kind of like what we're doing here, except we're looking at A, B, and C as 3 different people, like Alfred, Bruce, and Catwoman. So if I take A, B, and C and start the process of rearranging, I might switch the B with the C. Right. I could take the A and switch it with the C. Right. I can take this A and switch it with the B. Right. But maybe if I go back to my original setup here, maybe I wanted to initially switch the A with the B. And then from there, maybe I want to switch the A with the C. So I'm just doing a little position swapping here. So I took the A and swapped it with the B to give this pathway. I took the A and swapped it with the C to get me down this pathway. All right. Ultimately, we're going to end up with a total of 6 arrangements. All right. So that's one way that we can handle it. Another way to handle it would be to make a tree diagram. All right. It's not the world's most complicated tree diagram. So, because if you don't like listing out sample spaces like we did here, but you do like visual approaches, the tree diagram might be the way to go. Because what we would do is we would establish how many different ways you could lead off your line, and then list those values. So my line in my position 1, any person A, B, or C could occupy those positions. All right. Position 2, because we're dealing with people here, you can't occupy, a single person can't occupy the same or 2 different positions at the same time. All right. So once A is placed in position, then only B or C could occupy the second position. If B occupies the first position, then only A or C for the second position. And if C occupies the first position, only A or B for the second position. And then it gets much easier, because as you expand your tree diagram, really 2 things, 2 possibilities. One is that it's going to get simpler and simpler as you extend from left to right, or it's going to get more and more complicated depending on what it is you're trying to do. But when you're restricting the number of people that could occupy different positions down the line, it does tend to get simpler. All right. So position 3, A and B are already placed if I follow this branch of the tree. So that leaves only C for the remaining limb, if you will. All right. If A and C are placed, then only B could occupy the remaining position. If B and A are placed, then only C. If B and C, only A. If C and A, only B. If C and B, then only A remain. All right. So not quite in this, it's definitely not in the same order as what we have over here, but all the elements are still there. So if I look at this, I'll actually extend my highlight. ABC is what we started with. Then we add ACB, then CAB. So I really looked at this branch of the tree, or this pair of branches of the tree, as we worked our way down the line over here. All right, and then went back to those. But it doesn't make a difference how you write it, as long as you account for every different possible arrangement. Still 6 arrangements. All right. Now, another way that you could do it would be to use a factorial. All right. So what this means, or what this actually simplifies down to mathematically, is 3 with an exclamation point. All right. When you write a factorial, if I say 3 factorial, the calculator can handle it. But if I say 3 factorial, I'm saying 3 times 2 times 1. All right. So 3 times 2 times 1. What you're dealing with when working with a factorial is whatever number is in front of the exclamation point, that's where you start, and you end at 1. All right, all multiplication. There's another symbol that allows you to add, consecutive values, but that's something else. All right, we've actually done stuff with that. That's really like the summation symbol. But a factorial is really a similar idea, just with multiplication. All right, and if I carry out this product, 3 times 2 times 1 is equal to 6, I get my 6 arrangements. All right. So if you know how many things are to be arranged, you just slap a factorial on at the end, and you'll get the number of arrangements. So if I go in the NumWorks calculator, you go into let me put the 3 in first. You go into the toolbox here, which is right below OK. And you'll see a lot of different possibilities here. The more popular things. You go down the line, you'll see one for probability. I'll get to that in a second. But you go down the line, you see all this stuff. All right. A lot of stuff we don't need, but list is going to be pretty useful. Matrices and vectors, we'll get to that later in the course. But right now, probability. All right. So right there, and this is the reason why I mentioned the name of this, is combinatorics. you'll know to look in this particular menu. And I'll take that as a typo, because if I wanted to correlate with the NumWorks calculator, so that makes sense. So you can hit the right arrow or OK. Brings you into the combinatorics menu. You have combinations, permutations, and right at the bottom here is factorial. All right. So if I select that, it brings up an exclamation point on my home screen. Hit enter, gets the job done. All right. So when it comes to, well, anything in the combinatorics subunit or topic. Whoa, this got updated. Anything in the combinatorics part of the unit, you could use the calculator without restriction. Right. There are some things that I'll show you to do by hand. I'm just going to leave this down here. But that's really only for instructional purposes, so that you learn why things work the way they do. All right. But when it comes down to the nitty-gritty, we do it in the calculator. You see that there's a general rule there. We'll come back to that in a little bit. General rules are wonderful. They're rules that work in all cases. But if you have a calculator that knows the general rule and it can apply it for you, that's even better. All right. So that's what a factorial is. What I want to do is I want to create a restriction or apply a restriction to that factorial. All right. That's going to get us to the concept of a permutation. But again, let's do a guided example. All right. A line consisting of 2 people must be arranged from a group of 3 people. All right. So it's trimming it. It's saying, I have 3 people, but I only want 2 of them. All right. So that's where I look at, I have, like, forget about people for a second, the flowers, 3 different types of flowers. And I want to create an arrangement, but only using 2 of the 3 available flowers. All right. That's what's happening here. So I still have my people, my A, B, and C, but I only want them in groups of 2. All right. So 2-person arrangements. So A, B, that would be one possibility. AC, BA, BC, CA, and CB. Still 6 possible arrangements. All right, so still 6 possible arrangements. And in fact, in a tree diagram, all I'm really doing is taking the tree diagram I created before and ignoring the last position. All right, so it's still 6 possible arrangements. So it's kind of like, well, what about that last person? Like, is there any impact that last person has on the whole situation? Well, if I look at it from the perspective of a factorial, if I did 3 times 2 times 1, all right, so what normally would be 3 factorial, you ask yourself, well, what impact does the 1 have on anything? Well, there is no impact, because anytime you multiply by 1, there's no change in the number. All right. So this is the same as taking 3 and multiplying it by 2 and ignoring the 1. All right. So 3 individuals followed by 2 individuals per each of the 3 individuals that you started with. All right. This brings us to a concept called degrees of freedom. When you have a set or a sample of individuals and you have some known, I lost the word there for a second, constraint. Oof. And if you have some known constraint, then typically what'll happen is you'll have control over all but one of the values that make up that sample of individuals, right? Because after I've placed 2 out of the 3 individuals, this is all decided for me. All right. This is all decided for me. All right. All this stuff here is decided by me. So a degree of freedom is really just kind of exactly that. You know, if you say freedom, I mean, it means a lot of things, but in the case of math or anything academic, that means you have control over things. You know, you have control over your own destiny. You know, you don't control anyone else, but you can control any decision that you're entitled to make. You can make that decision without restriction. Okay, that's the concept of freedom. In this context, you have freedom to choose who's going to be in the first position, who's going to be in the second position based on who is in the first position, but then you lose your freedom to choose after that because all the necessary decisions have been made that you can make. Nature takes over at that point, right? So you placed A and B, so all you have left is C. All right. Now, if I change the phrasing of this, instead of saying I have 3 people that I want to be arranged in a line, just like in example 1, if I change that to say I have 3 people that I want to arrange in a line, but only occupying 2 positions, but I also want to have one other person who is going to help me with a chore or some kind of task. Right. So I have 3 people available. I'm going to line up 2 of them, and I'm going to ask one of them to go down to the principal's office and deliver a note. Right. That third person is not part of the line, but it is part of the activity. Right. So in the case of the permutation, if I'm looking at, 3 people must be arranged in a line. I'm sorry, 2 of them arranged in a line of 3 people. It's basically saying how many people can occupy the first position, how many people could occupy the second position, and how many people would be left out of the activity, right? So in this case, it would amount to the same thing, right? It'd be the same number of arrangements because this extra individual here is also accounted for by saying, well, they get to go home. I also kind of look at it like a good example would be you're participating in a race, and the person who finishes first gets a new car. The person who finishes second gets a new flat screen TV, and the person who finishes third gets nothing. All right, and there are 3 people that are participating in this race. Right? How many different ways can you give out a TV, a new car, a TV? Or you could say, how many ways can you give out a new car, a TV, and then nothing? It's really the same question, right? Now, in terms of a shortcut in the calculator, that's where the NPR notation comes into play. All right. So you see the NPR down here. I'm going to zoom in a lot real quick. This is the number of individuals available. And this would be the number of individuals in each arrangement. All right, so number of individuals that are available, number of individuals in each arrangement. All right, so the typical way of explaining it, historically has been if the order matters, then you're dealing with a permutation. But I found that people really don't know what the heck I'm talking about when I say that. Right. What I would say is if your position in a particular group is important, then it's a permutation. All right, we'll get to combinations in a second, but the example of running a race, and there could be 100 people in a race, but if you get a different prize for each position that you finish in, let's say top 10, then it does matter in what order you finish the race, right? Because if the new car is for the winner, and the big screen TV is for the first loser, and then the second loser gets something else after that, and the third loser, and so on, all the way down to the ninth loser. So the person who finishes 10th, then oh boy, the Islanders just scored. All right. Yeah. Well, anyway, it does matter in what order you finish. Now, if I tell you that there are again 100 people running in a race, and anyone who finishes in the top 10 is going to get $100 gift card, then in that top 10, it doesn't matter what order you finish in, as long as you make the cut. All right. Speaking of making the cut, another example of something that would not be a permutation would be if you're trying out for a team. There's 30 people trying out, but they're only going to take 20 on the team. You don't care if you were the first person on the list, or maybe for pride, I guess, but you don't care if you're the first person on the list or the 20th person on the list, as long as you're in the top 20. All right. So if you were the fourth person that they select, great. It doesn't matter. You're on the team. Now, if you're being drafted into the NFL and you're the first person selected, you get more money. If you're the second person selected, you get a little bit less, but more than the third person and fourth person. So that's a case where the order of the arrangement is really important, right? So any instance where you look at the order of the arrangement, the order within or position within the group having a meaningful impact on things, you're dealing with a permutation. Now, in terms of the calculator, it's in the same menu. When I want to do something like basically this, we'll go into that combinatorics menu. You'll see permute. All right, this is the old TI notation for it, but it's the same. Well, actually, that's a different example. We would say permute, and then input the n value, and they say the k value. All right, so I'll make a little note here that this is always n, but this is sometimes k. All right. The standard way of representing it is to say R, but sometimes, as you can see in NumWorks, we use K. All right, so I'd put in 3 here, 2. Again, the 3 represents the number of individuals available, and the 2 represents how many are in each arrangement. All right, so I'd go 3, 2, close it up and hit OK, and it'll give me the 6. All right. So, different calculators will do different things, or I'm sorry, do the same thing, but in different ways. If you just Googled what is 3p2 and maybe throw in the word permutation, it's going to tell you. This is not privileged information. It's stuff that all calculators can handle. Right. So you kind of rely on that. Right. And again, there's the general rule. I'll get back to that in a little bit, only because I think it's kind of fun. It's a little computational, not something I would put on a test. Like when we talk about general rules, it's only for learning purposes. But yeah, it's worth kind of diving into a little bit. All right. Numbers 3 and 4 are all leading up to the combination concept. All right. So 5 students are in a class. Determine the number of 2-person groups that could be generated from the 5 students available. All right. So if I say, in a class of only 5 students, which would be a miracle because their class sizes are never that small, but I want you to get into groups of 2, which really isn't going to happen because there's going to be one person without a group. But if I want to determine the number of 2-person groups that are possible, I wouldn't care what order I selected the individuals. So if I have individual A, that's not a marker, A, B, C, D, followed by E. All right, so Alfred, Bruce, Catwoman. I'm gonna go with Dent for Harvey Dent and E for Edward Nygma. So all these individuals are going to be placed or could be placed in a group of two, right? So if I'm placing, let's say, A and B in a group together, it would not make sense for me to then turn around and say, okay, we got Alfred and Bruce in one group. Bruce and Alfred are going to be in another group. Be like, no, you already placed us in a group. We don't need to be, you're not going to put us in another group. We're already in a group. All right. So we wouldn't reverse the order like we would for a common permutation. So up here, we had A, B, and BA. We wouldn't do that here because I don't care about the arrangement. You don't get a special prize for being the first person I named to be in the group, just like you don't get a penalty for being the second person named in the group. All right. So once you've established the grouping, then you move on to a unique grouping. All right. So I did A and B here. So now I'll do A and C. That's another possibility. A and D. A and E. All right. Now I'm going to move on to B. If I work backwards here, I'm going to get BA that I already have that. So I'm going to ignore that. I'm not going to put a person in a group with themselves. That would not be a group of two in a practical sense. All right. So I'll move on to B and C, B and D, B and E. Then I'll start with C, C and D, C and E. And then the only other possible grouping that you could have would be D with E. Every other possible grouping would be a repeat of something that we already have here. You can also do it with a tree diagram. And even though it will get simpler as you go, it's still going to be pretty beefy. Right. So in this case, listing out a sample space may be more practical. Right. But ultimately, the reason why we're doing this is so that we can come up with the number like 6 for the first two examples without actually having to list out all the permutations and combinations. All right. So what I have here is a set of 10 combinations. All right, we'll have 10 combinations. And really, it's unfortunate that they took that lock, the one that's called a combination lock with the dial on it, and you put 36, 25, 42, like it's not a combination. Those are permutations. Because if I tell you the code is 157 to get into that lock and you put in 175, you're not getting in. All right. So
I have a
you need to
question.
correct. Yeah, sure.
Sorry to interrupt, but what about DB?
DB is the same as BD.
Oh, okay. So you wouldn't put that?
Right, because it's already been
Okay.
accounted. Good question. So 10 combinations is what I'm working with here. Again, we need an easier way of doing this. We could, I suppose another way to do it would be to list out all the permutations, every pair of values in either order, and then just cross off the ones that are duplicates. That's even more time consuming. All right. But if we use the combination function in NumWorks, that's the one that says NK. All right, that's for a combination. The N is the number of individuals available. I'm basically going to write the same thing that I wrote up here. So if you don't want to write it again, I understand. Number of individuals available. Number of individuals in each combination. My handwriting has gone out, down the drains, out the window. Overboard. Each combination. All right, so 5 students in a class, I want 2 people in each combination. So this would become 5 with a 2. I don't like saying 5/2 because then it makes people think of fractions. It's not, it's just a different form of notation. But it opens little entry fields where you can put the 5 here, hit the down arrow, put the 2, and then hit OK, and it gives you 10 combinations. All right, so the only challenge that you're going to be faced with here, because the calculator does everything for you, is knowing which scenario, if you're given a problem, which one is the permutation and which one is a combination. All right, factorials are a special case of permutations. So, and I'll get to that in a little bit. You could actually solve a factorial problem with a permutation, and you could solve some permutation problems with factorials. All right, but the next example is really just kind of like an extension of this. It's actually pretty easy, except you wouldn't necessarily think that that's the case, right? Because it seems like it's actually getting harder. 5 students that are in a class determine the number of 3-person groups that can be generated from the 5 available students. All right, so I could list out the sample space here, but what I'm actually going to do is take the one that we just did, if it'll let me. No, you see it does that now, and I don't know, that's one thing in the update that they messed up. It doesn't want to let me copy from page to page. Let's see. I don't want to do screenshot. I'm going to try to copy again. Maybe I'll just do it kind of in a more extreme location. Oh, okay, that actually worked. I think it was because I was towards the top of the page, but this is 2-person groups. All right, which wouldn't seem like it's what we need, but it gets the job done. All right, because, and I'm going to move some things over here, and I know it's not, you're doing a pencil and paper, it's not as student friendly, but I'm just going to tuck this off on the side here for a sec. So if you have a 2-person group out of 5 people, these are the keepers. All right, starting off with AB. So I'll say the keepers. Keeps, I guess that would work too, but keepers. And you would also have, if assuming that it's person A, B, C, D, and E, if I'm telling you that I'm taking 2 people to be on my team or in my group, that means that I naturally have a group of leftovers. All right, and that would be C, D, E. All right, so if AB is on the team, like I'll just use the making the team analogy, or you have a team of 5 people and you want to name 2 of them captain. All right, A and B are the captains. Well, I created a group of captains, but I also indirectly created a group of people who are not captains. All right, so AC, BDE, that would be another group of leftovers. AD, BCE, AE, BCD. These are all my leftovers. All right, so for every group of keepers, I have a group of leftovers. right? So if I'm looking at, and I got BC, BD, BE, those are all my keepers. I'm going to have a group of leftovers again. All right, so BC is my group of keepers. My group of leftovers would be A, D, and E. If BD is my set of keepers, then I'm going to have A, C, and E. If B and E, A, C, and D. These would be my leftovers. Looking at C and D, I'm sorry, C, D, and CE. If CD is in my group of keepers, then A, B, E would be my group of leftovers. CE, A, B, and D would be my group of leftovers. And then finally, if DE is my group of keepers, then A, B, and C would be my group of leftovers. All right. In the end, you see that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 leftovers, or 10 groups of leftovers. All right. So my group of keepers, those are 2-person groups. My leftovers are naturally 3-person groups. So for every group of 2, there is a corresponding group of 3. All right, so sometimes you could reason out the answer, but if you're getting into the notation, the combination notation would be to use that funky bracket thing. We would say for this 5 and 3, that's going to be the same as 5 and 2. You see, I always try not to make it a fraction. I always end up doing it at some point. All right, both of which give a result of 10. And I can demonstrate toolbox combination 5, 3, same result. All right, gives you a 10 anyway. All right, that's a complement rule. What it tells us is that if you have n, so I'll make it a rule here, nk for a combination, that's going to be the same as n minus k. All right, so basically, I mean, if you're looking for just more or I'll say less notation heavy way of understanding that, if the 2 numbers on the top are the same and the 2 numbers on the bottom add to the top number, then the results of the combination would be the same. So another example would be like 10 on top, 7 on the bottom would be the same as 10 on the top, 3 on the bottom. We'll do that real quick. 10 up top, 7 down low. 10 up top, 3 down low. Both give you 120. All right. I want to check something real quick because I'm still learning more and more about these numWorks calculators. I want to see if it does something. If it does, I'll explain. If it doesn't, pretend I'm not doing it. Yeah, syntax error. Okay. Yeah, because some calculators will test whether 2 values are equivalent to one another just by putting an equal sign in between. This apparently is not one of them, or at least not in this app. All right. You see all these formulas here. They're pretty kooky. So yeah, I wanted to kind of take you through a little bit of it. There are some shortcuts. I mean, the ultimate shortcut is using a calculator, but there are shortcuts that are a little bit more intuitive and manual, I would say. Something to bear in mind is the approach that you use should really kind of suit your needs. Some of you, you're done with math after this course, and some of you are going to take math until there are no more math classes to take. And that's typical. All right. So, and some of you are going to take more math classes down the line. You just don't know it yet. Yeah. So that's not something everybody wants to hear, but that's a possibility. All right. So if you're done with math after this course, you're probably just going to do everything on the calculator and be done with it. But if you're going to find yourself taking calculus classes and things like that, you're going to want to learn the by hand way of doing this. All right. You don't have to master it for this course, but you want to at least start developing some familiarity with it. All right. So the first one, 14p14. Again, something that could be done on a calculator, but I'm going to bring us all the way back to the rule, the general rule for permutation. I know it's kind of blurry now, but this guy right here, NPR, you could use K instead of R if you're kind of getting more familiar with that, is equal to n factorial over n minus r factorial. All right. So I'm going to bring that down here. So NPR, for the sake of consistency, I'm going to say NPK. And I'll make these all typos. Because I know some folks have been just dying to get some typo bonus. And so everywhere you see an R, just make it a K. Those are the only instances, but there's a few of them there. All right, so NPK is equal to n factorial over n minus k factorial. All right, so if I'm trying to do this problem by hand, I would really write it as, let me just kind of shrink it a little bit. There we go. I would write this as 14 factorial over 14 minus 14 factorial. All right. Now, it's not really an astonishing realization just yet. At the bottom, we have 14 factorial on the top, 0 factorial on the bottom. All right. Now, I'm just going to say for right now, for this very moment, I'm going to say that the rule is 0 factorial is equal to 1. I'll prove it to you later. Right. But there is a, I'll call it a philosophical justification or explanation for why it's equal to 1. And that has to do with how many ways you can arrange nothing. Because a permutation is a factorial or permutation is a type of an arrangement. How do you arrange nothing? Well, you wouldn't say no ways, because if I suppose how I define nothing would be important. If I say in my hand is nothing, how many ways can I present the nothing to you? I think I could only do it the one way. All right. So that's more philosophical, but I'll get to the computational in a couple minutes. So we're going to assume for now, you're going to believe me, that 0 factorial is equal to 1. And anything divided by 1 is itself. So 14p14 is the same as 14 factorial. Now, there's only so much you can do by hand, because if I needed to list out in order to find the product, in order to find the factorial, it would be here for a while. Right? It'd be 14 times 13 times 12 times 11, all the way down to 3 times 2 times 1. Right? That's a lot of stuff to multiply. And if you eventually ultimately have to multiply it, you'd probably just chuck it in the calculator anyway. So 14 toolbox. And again, folks, just so you remember, when you go into the toolbox in NumWorks, it brings you to the last menu that you were in. So if you need to get, a fresh start in the toolbox, just hit the back arrow. And then when you go in, you're in a fresh menu. It won't even bring you to the top unless that's where you left it off. All right. But you go to probability, combinatorics, and we want the one with the exclamation point. So 14 factorial, and you get this lovely looking number, 87178291200. All right, so you needed a calculator for it anyway, but the real reason I wanted to go over this is to drive home the idea that 14p14 is the same as 14 factorial. All right, so what that's telling me is that if the number before and after the permutation is the same, it's a factorial, right? It's an equivalent factorial. So it's kind of nice. And again, I mentioned before, this is for the sake of learning. So am I going to ask you to list this all out on a test? No, I'm going to just ask you what 14p14 is. Maybe it's a multiple choice question. And you just put in the one that looks like 87 gazillion and you're in good shape. But sometimes the act of typing something in the calculator takes longer than actually doing it out by hand. Now, when I say by hand, it could mean using a formula like this, or it could be knowing a shortcut, like 0 factorial is equal to 1. All right. So the NCK rule, I'll just jot it down here so I don't have to go back and forth. Oop, that moved on me. Let me make this 0.5. So NCK is equal to, I'll use the expanded form, n factorial over k factorial times n minus k factorial. I'm just going to move it over a little bit so it's a little bit more visible. All right. And I'll make this one the 0.65. All right. So if I want 5C0, oh, I neglected to mention this because we're using the NumWorks calculator. 5C0 is the same as 5 over 0, right? It's the same thing. I realized, I was like, wait a minute, I don't think I talked about the C notation, all right? So when I say this rule here, I can just move it over a little bit. That's the same as saying n over k. Those two forms of notation are used really interchangeably to the point where I gotta say, in all honesty, I never used this bracket notation here until I was well into my teaching career. It was always the C notation, the way I learned it. So my first thought was like, what the heck is that? And then I was like, oh, it's just a combination. It means the same thing, right? You're actually going the other way where you see this and you say, what the heck is that? It's just the bracket notation. It means the same thing. So when I say 5 over 0, I'm calling the 5 the n value and the 0 the k value. So 5 over 0 would be 5 factorial over 0 factorial, coming back to that again, times 5 minus 0 factorial. I'm going to leave the factorial notation alone for a second because something really nice is about to happen. 5 factorial up top. 0 factorial goes to 1. 5 minus 0 is 5. So 5 factorial. All right. 1 times anything is the anything. So 5 factorial over 5 factorial. Anything divided by itself is equal to 1. All right, so I mean, it's a lot of writing just to get to a kind of a simple idea that any combination, so anything in the form of NC0, which is the same as saying whatever that number is over 0 is going to be equal to 1. So that's a rule. So these 3 things are equivalent to one another. That's what I meant before when I said sometimes doing the work with a shortcut or doing it by hand will be quicker than actually typing it into the calculator. Especially if I were in your position, I'd be, as I'm getting more and more familiar with the numworks, it'd be like, oh, where's that toolbox again? Oh, what am I looking for when I get into the toolbox? How does this work? If you just look at it and say, oh, the bottom number in the bracket form is 0, or the number that comes after the C is equal to 0, the answer is going to be 1. That's pretty nice. All right. It's the same idea for C, for question C. It looks very different. Oh, actually, speaking of looking very different, the font here is very inconsistent. That's also a typo. I want these fonts to be consistent with one another. All right, so if somebody wants to claim that as a typo, remember you can get up to 3 bonus points for typos per unit. All right, so some people are kind of cruising along with that, and some people are like, what are typos? What are you talking about? So anyway, 14C14. If I'm using this rule here, I could write it as 14 over 14. That's why I don't stay over. Or I don't want to say over. I gotta be reasonable. I've said over many, many times already. All right, but I've instinctively, when I say over, I write over as in a fraction, and it's not a fraction. All right. So this would be, I'm calling this my n value. This is my k value. So 14 factorial over 14 factorial times 14 minus 14 factorial. A lot of 14s and a lot of factorials. All right, but it's going to clean up nicely. 14 factorial up top. This 14 factorial that we're stuck with, but 14 minus 14 is equal to 0. So that's going to be times 0 factorial, which I still haven't proved it yet, but we're taking on faith that that's equal to 1. So 14 factorial over 14 factorial times 1 is 14 factorial over 14 factorial. Anything divided by itself is equal to 1. So you get another rule. More rules. All right. If the number before and after the combination notation, if you're using the C notation, or if you're using a bracket notation, if the number top and bottom is the same, the result is equal to 1 also.
So basically, if we see one of those, like it's the question B, and you put 20, and then you have the C, and then you have 20, it's going to be 1.
Exactly.
Do we have to show the work or be
Nope.
okay? And same thing with 0.
Exactamundo.
Okay, thank you.
No problem. All right. For D, I'm going to go with shortcut as the word of the day. Shortcut. I believe that's one word. It's a compound word, if I'm not mistaken. Shortcut is the word of the day, because that seems to be the theme anyway. So for D, 7C1, we could think of that as the 17 over the 1 without a
You said
fraction.
17. You mean
I did
7?
say 17. I have no idea why. The 7, thank you. So that's going to be equal to 7 factorial over 1 factorial times 7 minus 1 factorial. Yeah, so apparently sometimes I make verbal typos, verbalos. Anyway, we can clean this up a little bit. 7 factorial over 1 factorial times 6 factorial. Now there's more we can do with this, but I'm gonna sit tight on that for a second and move on to E, because there is a relationship between these two. And it has to do with that complement rule I talked about before. But for now, let's just jump into it and see where it takes us. We're gonna have 7 over the 6. We're looking at 7 factorial. It's not locking into a fraction bar for some reason. But one time I want to make a fraction bar, it's not working. 6 factorial over 7 minus 6 factorial. All right. So 7 factorial over 6 factorial, 7 minus 6 here is equal to 1, so times 1 factorial. All right, if you compare our answer, well, it's not even an answer yet, but if you compare our responses to D and E, you see
It's reversed.
Yeah, but in multiplication, we can reverse it and we're still going to get the same result. All right, so whether we look at 7C1 or 7C6, we're going to get the same answer. All right, that was that complement rule I was talking about before that tells us that if you have N and K, that's going to be the same as N and N minus K. All right. So the examples are D and E, but I still have to figure out the number. All right. So that's one quick aside. There is actually another rule that comes out of this, and it's kind of cool. All right, actually 2 more rules. So nice little shortcuts, but I am going to have to expand it out a little bit. All right. The 1 factorial is equal to 1. I mean, that's less a rule than it is just, I don't want to say common sense, but it's like if we're defining a factorial as multiplication starting with a given number, declining until you get to 1 and then multiplying it, it would beg the question of, okay, so what happens if you're already at a 1? You have nowhere to go. The answer is just 1. All right. But the 7 factorial could be written as 7 times 6 times 5 times 4 times 3 times 2 times 1. And the 6 factorial could be written, well, all of this again. In which case you could do some nice cancellations, because anything divided by itself would be equal to 1. And
So
you'd
is,
be left.
is the answer 7 then?
It is. And that actually leads us to another rule, because if the number that comes after, so we had the number coming after the combination of 0 gave us a 1 for the second example, but if the number that comes after the C is a 1, what would happen? You actually get the number that you start with. So if I say N with a 1, the result is just going to be whatever the N value is, which is kind of cool. All right. And then alternatively, because we know this is the same calculation over here, this is going to have to give a result of 7 also. What was the relationship there? There was only a difference of 1 between the 2 numbers. All right. So we have another rule. So we got all these rules, none of which you actually really need, because you could always do it on the calculator, but it's just nice to know. If the difference between the number on the top and the number on the bottom is 1, then the result is just whatever the number on the top is. All right. So again, I can go to my combinations type in a 7 on the top, 6 on the bottom, and hit OK, I'll get 7. And you don't even have to do any of this stuff here. But if you recognize it, you don't even have to look at the calculator. And I'll just say it. Sometimes we learn for the sake of learning. It's just, I'd like to understand some things. So we talk about it. All right. Now, and all these shortcut rules are on the next page, you can see here. But the pièce de résistance, F, which is the 0 factorial. Now I mentioned I would demonstrate to you how that works. All right, instead of the hand waving, literally, I use the hand waving demonstration to justify it. Sorry, I got heartburn. We're going to use a rule. The general rule here, n factorial is equal to n times n minus 1 factorial. It's really kind of, sometimes it feels like it's a silly rule, but it's actually pretty powerful. I can actually justify this rule to you really quickly over here. So for example, if I want 7 factorial, I could write that, because this is my n value, as 7 times 7 minus 1 factorial. All right, which is the same as saying 7 times 6 factorial. Which doesn't seem to serve much of a purpose, because then I would have to look at 6 factorial, which would be my new n, which would be 6 times 6 minus 1 factorial, which would be 6 times 5 factorial. And then I'd have to look at the 5 factorial and see where that goes, and the 4 factorial, and 3. Eventually, it would expand out to the 7 times 6 times 5 times 4 times 3 times 2 times 1, which is what we did over here. All right, but what I could have done, and I'll just take this one for example, I could have written 7 factorial as 7 times 6 factorial. And then I have the 6 factorial times 1 factorial on the bottom. The 6 factorials would cancel, and you'd be left with just 7 without having to expand it all out like we did over here. All right, so this is the benefit of something like that. But again, I'll just keep going back to that shortcut idea. Yeah, we have shortcut rules, but you have the ultimate shortcut rule over here with the calculator. All right, so doing this number crunching, because I'm sure it's going to come up. Do we have to do it this way on the test? No. Calculator. Use the calculator. This is for the sake of learning. All right, so without further ado, demonstration of why 0 factorial is equal to 1. So if I try to apply this rule here, I circled the wrong thing, this rule here to the 0 factorial, what I could do is I could let the 0 be the n value. Now, this is the incorrect way of doing it, but you don't necessarily know that until you try it. So I would say 0 factorial is equal to 0 times 0 minus 1 factorial, right? And what you end up with here is a problem. This is not possible. All right. When you're dealing with counting, we're only working with whole numbers. All right. So, and in fact, typically we say non-zero whole numbers. So natural numbers, counting numbers, if you will, counting numbers. All right. So how many elements would make up a sample space? We could say, well, there's none in the sample space. That's a possibility. But if there are elements in the sample space, there have to be at least one of them. All right. So there's no way you can end up with a negative. All right. So that's a break in the system. So the clever way of handling this would be to try 1 factorial using the same rule where the n value is equal to 1. So 1 times 1 minus 1 factorial. 1 minus 1 is equal to 0. So I have 1 times 0 factorial. 1 times anything is anything. So that gives me a 0 factorial. All right. So the left-hand side of this equation is the n value factorial, the 1 factorial. We just demonstrated that 1 factorial is equal to 0 factorial. 1 factorial we know is equal to 1. So therefore 0 factorial is equal to 1. Right. So it's a little mini proof that demonstrates why 0 factorial is equal to 1. It's just that I don't think, yeah, it wasn't, I mean, I learned about combinatorics in high school, but it wasn't until college that somebody really explained that to me. That being said, I was absent a lot in high school, so they probably explained it. I just wasn't there for it. But yeah, it's something that always bothered me. Like, how could 0 factorial not be equal to 0? I mean, it's multiplication and it's got 0 in it. So how does this even work? So I lost faith in this entire branch of mathematics until I got that that explanation, and then off to the races. Right. So yeah.
Sorry, I have a question. So
Sure.
0 factorial is equal to 1?
Yep.
And if you have a question like this in the test and I have to, get the answer, we just don't have to do the whole process, right? Just put the 1.
Right. Yeah, you can just put the 1. And if you forget that it's equal to 1, you put it in the calculator, it'll tell you it's 1. You get a bunch of different ways. You don't have to do it out by hand though.
Okay, got it.
So yeah, just looking at these shortcut rules, they're kind of there for your benefit. If you end up not using them, then that's fine too. You use the calculator, but sometimes just being able to recognize, oh, it's something C0 combination with 0 groups, right? That's got to be equal to 1, and just move right along. And sometimes you go the other way where it's like, all right, let me try doing it in my head. But, it's a test. So let me check it on the calculator. Oh, good. Satisfaction of knowing I know the material. All right. So I'm going to stop the recording. Oh boy, stop the recording.